For our program tonight, we have Dr. Wes doing a presentation on the Vera Rubin Observatory, which recently came online and within like 2 weeks had sent back like 10,000 pictures or something like that. So, I mean, really incredible. So I'm really anxious to hear updates on how that's doing. So thank you, Wes.
Yeah, exactly. Come on. All right. So thank you, Valerie. Congratulations to John again. So Valerie asked me to do kind of a short version of this talk because we knew we had other festivities going on. I think the air conditioning is out in this room too, and so that's probably going to make me go even faster. So if I apologize if I'm speeding through the slides. I gave this class in July of last year, right after Rubin came online. And it's actually, it's kind of interesting because, you know, with Artemis happening last week, I know I've been talking about Artemis for a decade, right? And talking about and trying to get people hyped up about it, and then it finally happens. The same kind of thing is true about Vera Rubin Observatory. The astronomical community has been talking about it for well over a decade. And the fact that it's online now and we're just getting to the point where we're starting to get flooded with data is really exciting for the astronomical community. We actually just hosted a astronomy group over the weekend. Friday we had our conference here, and then Saturday we had the second day of the conference over at NKU. That was a professional astronomical group. So we had folks from NKU and University of Kentucky, University of Louisville, UC, Ohio State, all presenting their research, and a lot of those talks were mentioning Rubin and all the wonderful things that are going to come out of Rubin. And so tonight we can fill ourselves in a little bit about why this is such a really revolutionary instrument. In a lot of ways, you know, you think of Hubble as an absolutely revolutionary instrument. Yes. You think of James Webb Space Telescope as a revolutionary instrument. Yes. Rubin is on that same level, even though it is a ground-based telescope. And hopefully after the presentation tonight, you get a feel for why that's the case. So its first images, as Valerie was mentioned, were shared on June 23rd of last year. It's an 8.4 meter telescope. That's a little bit deceiving. That's a big telescope. It is for sure a big telescope. But because of the way it's designed, it doesn't actually technically use all the space of an 8.4 meter telescope, as we'll see here shortly. And probably the most impressive thing, besides the size of the mirror itself, is the 3200 megapixel camera. So that is the largest digital camera that's ever been created. It's taking very large pictures of the sky, 10 square degrees. And it's basically taking images and then moving to the next patch of sky, take an image, next patch of sky, take an image. And it plans to image the full night sky that's available to it every 3 days for 10 years. Okay. And it's doing it in multiple filters. And so you're getting multi-filter, different colors, information from every single night. It's producing 20 terabytes of data every single night. And so for those of you who aren't computer inclined out there, right, you know, when you had those old school, not even like floppy floppies, let's not go all the way back to floppy floppies, the little ones, right? Those were what, 1.44 megabytes, right? And so 1,000 megabytes is a gigabyte, 1,000 gigabytes is a terabyte. This is in a single night taking 20 terabytes worth of data, and expected to take 60 petabytes, which peta is 1,000 times tera, over the course of its 10-year mission. So the name of the observatory is the Vera Rubin Observatory. That's after Dr. Vera Rubin, who passed away relatively recently in 2016. She is known for her work in the discovery of dark matter and the kind of support of the idea of dark matter. And just as a real quick recap of what dark matter is, or how her observations contributed to that, she made observations of the rotation rates of galaxies. And so you see a picture here of M31, and whether it's an elliptical galaxy or a spiral galaxy, in general, they're brighter towards the middle, as you see in this picture, and then the brightness fades off towards the edge. And if you assume that the light from a galaxy is coming from the matter, the mass inside of the galaxy, then what you would assume is that If there's a lot of light in the middle and the light tapers off towards the edges, that should mean that the mass in the galaxy is concentrated in the middle and tapers off towards the edges. Now, if that's the case, then galaxies should behave like our solar system, where the mass is concentrated in the middle and then not much mass out towards the edges. And that means that things that are closer in rotate faster, and things that are further out rotate slower, just like Mercury versus Pluto, for example. Instead, what we found when we actually started looking at the rotation curves of galaxies is that the rotation rate, which is what these points are, stays pretty steady way, way, way out from the edge of the galaxy. And so you can see in this picture here, even beyond where you're seeing the visible light of the galaxy, you're still seeing pretty consistent high velocities. And the only way that you can have that happen is if the mass isn't concentrated at the center, but spread throughout the galaxy. And so gravity is telling you that there's more mass there that you can see. If that mass isn't giving off light, then call it dark matter, right? We still don't know what dark matter is, but Rubin, one of its main missions is to figure out what dark matter might actually be, or at least to be able to help with the problem. And so here's a picture from earlier in her career. You can see actually here some of the plates down there at the bottom that have some galaxy images on there and back from when she was doing her original work. Now, if you ask anybody in the astronomical community, you know, they're calling it Rubin now, but when I was talking about it 10 years ago, everyone referred to it as LSST. The name Vera Rubin Observatory was only decided upon, I forget the exact date, but it's within like maybe 5-6 years ago that they switched and decided to call it Vera Rubin in honor of her work. It was originally called LSST, and that stood for the Large Synoptic Survey Telescope. Survey in the sense that, again, it's taking images of the entire sky over the course of just a few nights. They were able to kind of maintain that name LSST to describe the mission that it's doing now instead of the telescope itself. And so the mission, that 10-year mission that it's doing, is called the Legacy Survey of Space and Time, because of course, when you're taking pictures of these objects, the further away the object is, the further back in time you're looking. And so in a sense, this is a measurement of a survey of space and time. Now, it's not the first survey out there. We've definitely had lots of surveys in the past, and there's really way too many to mention, but these are a couple of the big ones that astronomers have been using and still use today. There's SDSS, which stands for the Sloan Digital Sky Survey. This covers a significant portion of the sky. It was all taken by roughly the same instrumentation, the same telescopes, and so you have kind of a commonality between all the different pictures. There was PanSTARRS, which is panoramic, I looked it up beforehand, panoramic survey telescope and rapid response something. I was also, so Dave, where'd you go? Dave was one of the few that actually tuned in to some of the talks from that research conference the other day. And of course, it's just all acronyms, right? The research talks just end up being all acronyms. But these are past surveys where they literally took pictures all over the night sky. In some cases, it was kind of just a one-time event. In some cases, they followed up with observations over kind of a regular time interval. But to give you a sense of perspective, there's Rubin down here. These are all 3 pictures of the same patch of sky. Here you are, Dave. You're right in front of me. And so this is the Sloan Digital Sky Survey. This is PanSTARRS. This is Rubin. And you get a sense of the upgrade that Rubin is. Again, big mirror, a lot of light gathering power. And so you can see those 3 galaxies kind of, these are 2 that are interacting here, but those are the ones that are in the foreground. You can barely make out some gas in between the galaxies here, but by the time you get down to Rubin, it's quite clear that all 3 of those galaxies are interacting. And then of course, the background just completely pops with galaxies upon galaxies upon galaxies in this image. And this is, again, just from them turning the telescope and camera on for the first time and saying, hey, what can we do? And boom. We'll see that here in just a sec. Yeah. So this is located down in Chile. So we were just talking with some folks about the possibility of going down and visiting. I don't know if they have, for some of these observatories, actual public hours or anything like that. But La Serena is a tiny little village. I actually got to go there in grad school because I went to the sister mountain of LSST, of Rubin, to do some observations for a week in Chile when I was in grad school. But both of them are accessed via La Serena. And the control, I guess the base camp, if you want to think about it that way, for the telescopes is down there in La Serena. And then you drive up to the mountains in order to actually take data at the telescopes. But this is now, it's an almost complete picture of Rubin. It's done now, but this still shows some construction equipment there, but that gives you a little bit of a sense of scale because you got some trucks parked down here. And of course, the telescope is housed in the dome right there. Cerro Tololo, which was the sister mountain that I was at, I think was about somewhere between 7,000 and 8,000 feet. And so I think this one, Cerro Patron, is about the same. And so, yeah, not excessive, right? But still, you know, if you walk up a steep incline, you'll be huffing and puffing. Here's another perspective, and again, you can see Chile is, of course, you know, a hotbed for astronomy now, just because they've been very cooperative in terms of their partnerships with a lot of U.S. institutions. This is a National Science Foundation instrument funded by a couple of different government agencies, Department of Energy, things like that. But there's been telescopes and facilities popping up, of course, all over Chile because the foothills of the Andes serve as a really, really nice site. You're above the cloud layer in a lot of cases. Of course, some observatories are also being built there in the Atacama Desert. You got very, very dry conditions there, driest in the world. But these are a little bit further north than the Atacama. The actual telescope itself is the Simonyi survey telescope. Simonyi is the name of some very rich donors that put a lot of money towards the Rubin Observatory, and so the telescope was named in their honor. And this is, of course, a schematic view of the telescope. And what you will see kind of at different angles and kind of broken apart here in just a second. But one thing I want you to note is the very short and compact design of the telescope. Even though it's got an 8.4 meter wide mirror, it's very short and compact, and that was very intentional because of the way that they want to use this telescope. And we'll talk about that here in just a sec. For perspective, right, so there's the kind of mirror blank for the main 8.4 meter, main 8.4 primary. And this shows comparison of lots of other different telescopes that either have been built or are planning on being built. For example, Vera Rubin is right there. Okay? And notice that it shows it as this kind of donut. And that's because, like I said, even though it's an 8.4 meter wide mirror, it's not using that full surface because of the way the telescope is designed. We'll see that here in just a second. And all of these have a hole in the middle. It's just that Vera Rubin has a very large hole in the middle. For reference, some that you might know, where's Hubble? So James Webb is down here, Hubble is down here. These are obviously bigger, right? But James Webb and Hubble have the advantage of being out there in space and don't have to worry about the atmosphere. Some bigger ones here for the US, there's Gemini North on Mauna Kea, there's the Keck pair of telescopes out on Mauna Kea as well. And then these are ones that are planned. 30-meter telescope has been having lots of trouble for a long time. Don't necessarily know whether that's going to successfully go or whether it's going to be a US project anymore. And then the extremely large telescope, it says here planned 2028. Again, I think that's a little bit further down the road if it's actually going to happen. But it's a definitely large telescope by today's standards. So what about that design? So very different from the way Hubble is designed, the way Keck is designed, the way James Webb Space Telescope is designed. This is a 3-mirror and a stigmat. And so you have, instead of the 2 mirrors that you usually see for a lot of telescope designs, there are 3 main mirrors. So M1 is the 8.4 meter one down here. M2 is a secondary, convex, up here. And then M3 is actually made out of the same block as M1, but is differently shaped, right? Because by the time the light has bounced back and forth, the focus, the cone that the light is kind of in, you have to have a different shape here in order to bring it back to the camera where the camera is going to sit. And so light comes in, hits the main mirror, comes up here, hits the secondary, comes down here, hits the tertiary, and then goes through a set of lenses. And the lenses are even, this first lens right here is the largest lens that's ever been constructed. It's a 1.55 meter lens. So the reason for this kind of complicated design, and I am not an optics expert whatsoever, and so we can get Steve to tell us what's going on here probably. But all the other telescopes that we build, almost all the other telescopes that we build, want to focus in on a very narrow patch of sky and look at that very narrow patch of sky in intense detail. Rubin wants to look at a huge patch of sky. And when you try to get a very, very wide field of view with other typical telescope designs, you have a tendency to have very strong distortions at the edge of your field of view. But with Rubin, they wanted to maximize the clarity, the sharpness of the entire field of view. And this 3-mirror anastigmat design was the way to do that. And so you're sacrificing quite a bit of light collecting power because, again, the only thing that's collecting is this donut of M1, the mirror number 1 right there. But because of the design, you're actually getting an even picture, a nice sharp picture all the way out of the edges with this huge field of view. This is also showing these 3 lenses here are designed to do corrections for different distortions that happen no matter what kind of telescope you design, very similar to some of our Schmidt-Cass out there that have the corrector plate on the front. But again, they just had to be very, very large. And then the camera itself will again sit right here. It does sit right here. And that doesn't hurt anything because, again, no direct light is coming in along that pathway. And so this describes that mirror design and lens design a little bit, and also it talks a little bit about why they did this design and why it's so short and stubby. I think I've got it playing.
How does Rubin Observatory collect so much light and move so fast? We combined 2 different mirrors on a single surface to make Rubin's unique 8.4 meter mirror. Light hits the outer surface first, bounces up to a 3.4 meter secondary mirror, back down to the 5 meter inner surface, and then up to the camera. This mirror design gives Rubin enormous light collecting power, but also keeps it compact and nimble, so it can cover the whole visible sky in just a few nights.
So we mentioned the whole point is to be able to take a snapshot of the sky and then rapidly move to a new location. If you've ever, I mean, even some of the telescopes that we have over there, when you want to slew the telescope, when you want to move the telescope from one patch of sky to the next, you know, it might take 5-10 seconds depending on the motor, right? This is a gigantic, you know, large research class telescope, as big as they come, really. And it's designed to be able to take, say, 30-second image and then move to the next part of sky and be ready to take the next image in like 3 to 4 seconds, right? And that includes time for the telescope to settle down. Because again, one of the things that regularly happens is when you slew the telescope and it gets to its destination, there's usually some wobble and some, you know, vibration that happens as it settles down. The whole point of that compact design, the whole point of having M3 inside of M1 is to keep that compact, sturdy, and allow for rapid movement so that you can image the entire sky in 3 nights.
How does...
Whoops, there we go. To give you a sense of scale for the camera, right? And so here is, oops, I pressed the wrong button. Here is the camera standing next to a person, right? With a person standing next to it. And so you see the CCD, the charge coupled device inside there. And, you know, CCDs, charge coupled devices, are what most all modern cameras are made out of little picture elements, pixels, that are photosensitive, so that as light comes in, the more light that gets built up, the more charge gets built out. And then it reads that out. And basically a computer turns the amount of charge into a brightness on a screen. Now, Inside your phones is a CCD, right? And if we smashed open your phone right now, that CCD would be, smaller than your fingernail, right? But it's taking all those beautiful images that you all know that you can take with your modern phones nowadays. This is the largest CCD ever created, right? We'll see a picture of somebody holding a model of the CCD here in just a second. And that's giving you a sense of how big this imaging device is so that it can take very large pictures of the sky. There are the corrector lenses that we were talking about before. And then there's also, you see here, these colored filters. Those are astronomical filters, because when you're doing observations of astronomical objects, you usually don't want just unfiltered light coming through. You want to focus in on red light and blue light and green light so that you get a better sense of the color of an object, and then all sorts of other information that comes along with colors of objects. But if they're doing filters, right? If any of you all have your own filter wheels out there, you know that, you can do your pictures. There's a little filter wheel. It slides the filters in and out so that you can change the filters and change it from red to blue to green, whatever it might be. Well, this thing has the goal of being rapid. And so even the filter changing has to happen in kind of a unique way. And this is actually slow compared to the way that it actually happens in real time. But it is very quick about switching out filters as well. And you can see the wheel kind of rotates along the outside of the camera, and then it slides down the filter in front of the CCD itself. Oh, so yeah, it's taking multiple image for each slice and then moving on to the next multiple image. Yep. Oh, yeah. How? What's? Mm-hmm. So again, the ones inside your phones are smaller than your fingernail. This is how big the CCD is itself. 3.5 degree field of view. The apparent size of the moon in the sky is about 1/2 degree, right? And so this is showing how big the moon would be on this imaging chip. There are places here at the edges that are used for wavefront sensing and guiding. And so a way of the telescope to kind of maintain its pointing and also to adjust for any kind of deviations in the mirror. So it does have adaptive optics in the sense that it can kind of adjust its shape in order to be able to respond to the conditions. This is just kind of showing how a CCD reads out. Not very interesting. That's just how the charge kind of flows out of the camera. Again, biggest camera ever built, biggest lens to put in front of that camera, has a corrector for scale. And then, as Chuck was mentioning, right, this is the wonderful problem that Rubin is creating. There's going to be so much data. We already said 20 terabytes per night, 60 petabytes over the course of its 10-year mission. And then this is what's really crazy and what's just now starting to come online. 10 million alerts per night of anything that has basically changed in the sky. And so has it changed brightness or has it moved? And 10 million alerts per night that get sent out to the astronomical community so that they can follow up on that. 10 million things to follow up on, right? Obviously, what's that? That's every single night, yeah. 10 million new things that have changed, yeah. Right, correct, yeah. So one of the things that they're doing right now is kind of getting a baseline measurement of different things in the sky so that they can kind of use that as a template to see how things have changed when they go through the survey. Now, so as many people as want, everyone in this room could get these alerts. There's not, no. And so this is where this instrument being very unique, all this data, and one of the things, I'll talk about this here in just a sec. Let me save it for just a sec. And so about 100 different sky locations, 100 visits to each sky location per year, because again, it's kind of sorting through every night. Of course, since it's in the southern hemisphere, it's mostly getting southern sky objects. And so it'll be a little bit hard for us as northern hemisphere observers to follow up on some of these just because we've got limited access to the southern sky, but there's a decent amount of overlap that we can actually get to. 38 billion objects detected during the 10-year survey. And by objects detected, this is things that have been known before and new objects. And so 20 billion galaxies, 17 billion stars, 10 million supernovae, 6 million solar system objects. And to give you a sense, the stars and galaxies, a decent chunk of those are going to have been detected before. But supernovae are things that happen actively, right? And so this is 10 million new supernovae. And for solar system objects, we know of roughly 1 million, right? Asteroids, comets, Kuiper belt objects, all that kind of stuff. And so Rubin is expected to increase that number by about 5 million. So 5 million additional asteroids, comets, near-Earth objects, all that kind of crazy stuff. So this is what I was mentioning just a second ago. In order to process all that data, they had to come up with a completely new way of storing the data, because it's so much data. But then on top of getting 10 terabytes or 20 terabytes of data every night, they have to go through that 20 terabytes of data, see if anything has changed compared to a template, and then send things out to the astronomical community. And they've built a system that does that within 2 to 3 minutes. So within 2 to 3 minutes of the image being taken, the data has been analyzed, compared to previous templates, and then the alerts go out. Because the point is that some of these things happen so fast that if you want to do a follow-up observation, you need to be on that target within 10 minutes, a half hour, an hour. And so that's why there's the Stanford Linear Accelerator is handling a lot of that data analysis and the alerts. And it's a worldwide project in terms of where the data is being handled. And so this shows, obviously the telescope is gathering the data down here, but it gets immediately sent to the Stanford Linear Accelerator facility in order to produce those results. France is handling a lot of the long-term storage. Data release production is when you're not worried about an alert, but you're just worried about the data afterwards being produced. And so you see facilities in the UK, facilities in France, as well as some in Arizona as well. But of course, you needed a very, very reliable network in order to be able to do this. And so this is something that they've been working on for well over a decade now. And very unique to this project in the sense that you weren't just worried about building a telescope, you're worried about building the software and internet infrastructure in order to be able to handle all this data. So these little movies here kind of give you a sense of how it's going to be kind of plowing through the sky and be able to image. So it's showing how big one single image is, but then it'll kind of raster in between, or raster across the sky in order to get a full image of the sky. And then of course it'll just repeat that over and over and over again for 10 years, right? So you'll have roughly 1,000 full sky images over the course of 10 years.
The universe is a dynamic.
Oops, sorry. Go ahead. True. Yes, absolutely. Yeah. So the sky that's available at that time. Yeah.
The universe is a dynamic place, but how do scientists spot changes in the cosmos? First, they need to know what stays the same. Every night, Rubin Observatory will capture new images of the sky. Over time, scientists combine the many images of an area of sky, producing a template image of how that area typically looks. When new images are taken, the template image is subtracted pixel by pixel, leaving only the changes, a technique called difference imaging. Whether they're flashy like supernovae, on the move like asteroids, or pulsating like variable stars, Rubin will find about 10 million things that change every night in an epic feat of spot the difference.
And so that's basically the process that's happening when the data gets relayed to the Stanford Linear Accelerator facility and then processed, and again, in 2 to 3 minutes for every single image, being able to process any changes. So what are they hoping to be able to do? One big goal is to examine dark energy, not dark matter, but dark energy, where dark energy is that mysterious force that is causing the universe to expand faster than what it should, acting against gravity over time. And so this little video gives a idea of how we're going to
Where
search
are
for
we in the
that
universe?
information.
And how do we know? If we could make a detailed map of the universe, showing many different galaxies at different times, we could understand more about its structure and how it's expanding over time. Supernovae help us do that. Not only are they the cosmic explosions of dying stars, they're also great tools for measuring distances in space. Certain types of supernovae, called Type 1a supernovae, explode in a predictable way that allows scientists to compare them and figure out their relative distances from Earth. When you compare them, a Type 1a supernova close to Earth will look brighter than one far away, just like a flashlight in your face looks brighter than the same flashlight across the street. Type 1a supernovae are some of the brightest explosions in space, and that's how we can see them from billions of light years away. Their glow started traveling towards us billions of years ago, which means we can also use them to learn how the universe looked back then. With more observations of Type 1a supernovae in all directions, we can refine our map of the universe in both space and time. Scientists have been working on this project for a while, and they've found some surprises. When scientists in the 1990s looked at their space-time map, they noticed that the universe's expansion hasn't been slowing down over time like they expected. Instead, it's been speeding up. We don't know exactly what's causing that, but our best explanation is the existence of dark energy, a mysterious force pushing galaxies apart in the universe. Type 1a supernovae are great tools to help us learn more about dark energy, but they're rare to see in any one galaxy. For example, you'd have to wait about 500 years to see one in the Milky Way. We need more supernovae observations if we want to improve our cosmic map, and that's where Rubin Observatory comes in. Rubin will scan the entire southern hemisphere sky every few nights for 10 years, observing billions of galaxies and finding lots of Type 1a supernovae. Every few months, Rubin will detect more Type 1a supernovae than have been observed in all of history. That's a game changer for refining our map of the universe, learning more about dark energy, and maybe even revealing new cosmic mysteries.
And so if you know your astronomy history, right, Hubble Space Telescope is kind of responsible for learning that the universe was going through this accelerating expansion, and it was through Type 1a supernova observations. Hubble, of course, has the advantage of being outside the atmosphere, clearer views, but again, Hubble is designed to take images of a very small patch of sky. They occasionally do those large deep sky surveys, but that takes a whole lot of telescope time in order to be able to do that. The whole point of Rubin is that even though it's on the ground, this rapid response allows them to get millions of supernovae. That's going to help improve that picture. Dark matter, of course, is another big one because it's named after Vera Rubin. The idea here, you've probably heard about gravitational lensing, right? And most of the time when we talk about gravitational lensing, we're usually talking about strong lensing, where let's say you've got this big giant galaxy cluster in the foreground, and it's lensing the light of galaxies that are way off in the distance behind it. And so the light gets bent and amplified as it passes around that giant galactic cluster. Those are, of course, really, really interesting, and we study them a lot, and there's lots of good science there. But one of the ways to map dark matter is to use what's called weak lensing, where with a strong lens, the image of the galaxy is extremely distorted. It gets really stretched out, and sometimes you end up with multiple images of the same galaxy just due to the way that the light is bending. With a weak lens, you might have a galaxy that looked circular originally, and then just gets a little bit stretched out as a result of the lensing. And if that was just one galaxy by itself, you might not know whether, okay, is it actually lensed, or is it just that we're seeing it at a slight angle, right? It's not face on, maybe it's at a slight angle. But when you detect millions, billions of galaxies, you can start to do statistical analysis to say which one of these are likely caused by weak lensing, which one of these are just happen to be a weird orientation. And so it's that statistical sample size that will allow you to say, you know what, there's a lot of galaxies in this patch of sky that are exhibiting weak lensing. That must mean that there's a lot of dark matter in the way of those galaxies. They're mapping out what the inner solar system and the outer solar system is going to look like. Again, all these asteroids, we know of about 1 million right now, but this is going to add 5 million more. And again, when you've got that big of a sample, you start to get a better picture of how these asteroids interact with each other and the story that they tell for how the universe, or not the universe, how the solar system formed. So these are some maps kind of giving you an idea of like the million that we know right now. These are only going to get more crowded as Rubin does its thing. And then the other goal, well, another major science goal, is to kind of map out the Milky Way and galaxies, smaller dwarf galaxies that the Milky Way has gobbled up. And so a lot of these galaxies, when they get absorbed by the Milky Way, it's not just a one and done kind of slam into the middle of the Milky Way and you're gone. It's usually a multiple looping, stretching out of that dwarf galaxy so that you end up with these star streams all over around the galaxy. And when you have something as detailed sampling of the sky as this is doing, you can start to pick out those stars as something different from the normal Milky Way stars. And so you get an idea of the past history of the Milky Way and how it's absorbed some of those other galaxies. And then finally, just all the things that change, right? And so we already mentioned supernova. So there's supernova down there. Eclipsing binary stars. This is a cataclysmic variable where you have a star being having gas siphoned off onto like a white dwarf or a neutron star. You've got mergers, like binary mergers from a neutron star. You've got pulsating variables. There are lots of things that are changing out there in the galaxy. And of course, this is all about finding those changes. So the initial images that were released by Rubin back in the summer of last year, they wanted to release some spectacular pretty pictures because that gets the public's attention. This is the Lagoon and Trifid Nebula, which a lot of folks in here have probably tried to image or have imaged with theirs, but obviously Rubin's doing a spectacular job in terms of the amount of detail that you can see there. But this one again was, I mean, there is definitely cool science that you can do with this, but there was also just the pretty picture aspect of this to wow the public. And then this is kind of a full field image. So this is that roughly kind of 3.5 degree kind of image of the Virgo cluster. And so Virgo's coming up pretty high in the sky right now. It's getting to be galaxy system in a season. And Virgo has one of the largest superclusters of galaxies that are out there. And so this is a full frame picture. The majority of things that you see in there are galaxies. And then just to kind of show you the scale and the resolution here, this is a full frame picture, right? And then this little box is just indicating a subset of that. And you can see that even when you zoom in on that subscale picture, you have incredible resolution. And if you look closely at this image, you see just galaxies upon galaxy, right? There's a little beautiful spiral right there, all sorts of fuzzy ellipticals. And again, each one of those tiny little dots that's in the background is not a star, but a whole separate galaxy. And so this is the level of detail that Rubin is providing. Yeah. Find the stars. Yeah. Yeah. Yep. Yeah. So like right there, right, there's a star, but yeah. 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 So this is another update. So of course, an asteroid's going to be moving, and so it's the motion that's going to be detected. Yeah. But the really impressive part of this, right, it hasn't even really started its mission yet. Look at the timestamp down here. Night 1, 989 new asteroids. 1,035, or 30, you see the numbers. Yeah. But 7 nights and over 2,000 asteroids, right? Many of those new discoveries. This is showing three-dimensionally where they are. And so a lot of them in the asteroid belt, some of them out here classified as Trojan asteroids, and things that are all the way out here belong to the Kuiper belt, right? And that was a week of first look data just testing things out, right? Now, this is showing an update that just came out this month. And so that was that original video that we just saw a second ago, right? It's been doing some other observations, right? Testing things out as they get everything calibrated in the way they want to work. And they just released, I believe it's 11,000 new asteroids that they have found. And again, this is not from them doing the actual mission of imaging the full sky every 3 nights. This is them just testing things out over the past year. And with that little amount of data, they have 11,000 new asteroids just from testing out the instrument, right? And that kind of shows, again, the brighter ones here are the ones that were discovered by Rubin. This is from that same testing, transients, right? And so here's supernovae. Let me pause it for a second here. So here, for example, in the template image, the galaxy itself is over here, right? And then this is the new image, and that's a bright new star that was out at the edge of this galaxy that went supernova, right? And so it pops out where it wasn't there before, and it detects it because here's the template, here's the new image. It clearly detects a difference. Same thing here. You can see the galaxy, even though it's this tiny little smudge. But when you take the new image and you subtract the two, all of a sudden there's this bright spot that's out at the edge of the galaxy. That's a new supernova. Same for any of the others. And so it's really impressive that even if the galaxy is this tiny little smudge that's way off in the distance, it's going to detect the new supernova. So there's variable stars, supernovae. I think they've revised the number down to about 7 million alerts each night, which is still fine. Ran out of what? Yeah. This is also a very recent release. So from that first look, so the week worth of data where they discovered like 2,000 new asteroids, they've looked at some of those long enough that they can actually get light curves from those asteroids. And so this is just the asteroid's brightness versus how long it takes to rotate. So one rotation phase is just one full spin. And some of these asteroids, in particular this one, are rotating at a speed of like once every 2 hours. This is a particularly big asteroid that's about 700 meters across that rotates in less than 2 hours. And why that's interesting is because you can look at the rotation rate of an asteroid, and depending on its size, depending on its makeup, if it's rotating too fast, it will literally break apart, right? And so if this asteroid is stably rotating, that gives you an idea of its it gives you a clue as to its composition and its strength, right? Its internal strength. A lot of asteroids out there are like rubble pile asteroids, and if you spin those at any kind of decent rate, they just completely fly apart. And so by looking at these asteroids and actually being able to measure their rotation, they can get a kind of sample of the different composition of different asteroids out there in the asteroid belt. And some of the smaller ones are even rotating at like maybe once every 2 minutes or 3 minutes. So extremely fast rotations. Obviously, outreach has been a big part of this, right? The pretty pictures, and they've been doing a lot of PR. But citizen science is also going to be a huge part of it because, as Chuck said, if you're putting out 7 million alerts per night, there is not 7 million astronomers looking at those alerts. This is far too much data, which is a problem, but it's a good problem, right? Are we going to be able to follow up on every single thing that changes every single night? No, right? But you're going to be accumulating this data over time, and it's going to give the astronomical community, professional, and the amateur astronomical community, and then the citizen community, citizen science community, lots and lots and lots of things to work on for years to come. Yeah. Yeah. Uh-huh.
Get us working on citizen science. So I wanted you to take a look at the kind of stuff we can do.
Mhm.
We can do something like that. But take a look at what it's doing, what we do, and see if it's something you're interested in. And if it is, we'll work around and set up a workshop and we can get started on that.
And I can probably share the recording from the class that I had. And so this is one example. So The site is Zooniverse, which kind of sounds like a funny name, but it's a very professional site that has lots of citizen science projects from all sorts of different disciplines, but of course some of them are space-based. This is the one that Rubin has right now, where you sort through images, and basically you're asking yourself, does this comet have a tail or a coma? Does this thing that moved, right? Because asteroids are just going to look like a pinpoint of light moving, whereas a comet's going to have a tail or a head, a coma. And so you're trying to identify comets as opposed to asteroids. But Zooniverse itself, if I can go out to the main page, projects. Again, lots of them are biology and ecology based. But if you go down here to all projects and then scroll over, there's a category specifically for space. And you can see there's identifying supernova hosts. There's identifying the comets. There's sunspots. There's actually, these are looking at historical sketches of sunspots and counting sunspot numbers so that we can get a better record of how sunspots have changed over time. I actually, one of the conference presentations over the weekend was talking about how they use citizen science data in order to identify galaxy morphology. It's I'm nerding out here, sorry. It's a really cool project where they're looking specifically for galaxies that just happen to be overlapping each other in the sky. So let's say you've got a spiral galaxy here and you've got a spiral galaxy in the background. The light from the background galaxy is illuminating the dust from in the foreground galaxy, just like a light table. And it's a completely new way to study and examine those galaxies. Yeah. The Alcons, yeah. Oh, so in some sense, I think it's already being employed with that whole alert system. Yeah, yeah, and so it's one of the things that you might have noticed about AI, if you've looked into it at all, is that it actually has trouble identifying pictures, patterns with pictures. That's the whole reason why a lot of the things when you have to prove that you're a human involve pictures, because the AI isn't good, the bots aren't good at doing that. And so this is at least one case where the human eye can work a little bit better, but at the same time, AI is going to catch up. And oh, sorry, I'm putting the password up on the screen. Oh my gosh, where AI is going to work out a little bit better. Yes. And so they use the humans to train the AI in a lot of cases. You want? Okay, yeah. Valerie is making me take longer, so just keep that in mind. So yeah, sorry, let me go back to the comet catchers. And I haven't probably created an account on this computer, so it'll make me go through the tutorial, but that's actually useful. So it has a little tutorial here. And what you're looking for, hot or not, right? Basically, does it show a tail or does it not? And so the interesting object is always going to be at the very center of the field. And then you're looking, does it have a tail like that one does there? And sometimes it shows up a little bit better on the computer screen than it does projected. There's the coma or the head. And then sometimes you'll see things like fuzzy galaxies that might be posing as, or it might have picked out as a comet, but can you actually tell that it's not? And so, for example, this one right here is the first one that pops up. It's flashing between two images because, again, these are picked up because of their motion, right? And so what it's asking, do you see a tail or coma or dust cloud emanating from this object? Yeah. And so this one, yes, that one was easy, right? And yeah, if you are having trouble, you can also do done and talk, where you say, this one looked kind of weird for this reason, and there's somebody on the other end, an astronomer, that looks at them maybe every few days and goes back and gives you feedback on whether you were right or not. So this one, like Greg said, this one was technically a test. And so it says, hey, yeah, you actually did good. And so the more you do, the more it's just going to give you fresh new objects. And of course, it's not relying on your observations solely. It's building up a big database of everyone's opinions. And so it identifies where a lot of people have identified this one as having a tail. It kind of does statistics to see whether it's a reliable identification. I would say no on that one, wouldn't you? I don't know. Yeah. Yeah. This one probably got flagged because there's a distortion in the camera here. And so this image appears to be a little corrupted. And so I don't think that one was one. But yeah, that's an example of kind of the thing that you would do. I think I'm almost done here, I promise. Yeah, oh, look at that. There we go.